It's one of my primary interests to try to highlight the importance of indoor environmental quality in buildings at a time when our emphasis has shifted very strongly to conserving energy and protecting the environment from the consequences of using energy. I think those are both very important things, but the primary purpose of buildings is to create environments for people and processes that are safe, that are productive, that are healthy, that are comfortable. And I'm trying in this talk to point out that we need to keep that balance in what we do. We shouldn't value environmental protection and energy conservation less, but I think that it's clear that we need to do more in the area of IAQ. And this talk is intended to make the case for that in a number of ways, and to try also to indicate where we are in terms of reaching the potential of buildings to promote health and productivity of people. So if I turn my remote on, we can get going here. There we are. So these are the main subdivisions of the subject matter. We'll start out by reiterating the connection between air quality in buildings and the energy use of buildings. Then I'll spend a fair amount of time trying to give different perspectives on the importance of air quality. Then move on to some observations on what's done today to control air quality in buildings. Say a few things about technologies that exist now that can deliver better air quality efficiently. That's not really the main point here to talk about specific technologies, but I'll point out that we do have some of the tools in terms of systems. And the last part here is to point in the direction of where I think we need to go to be able to properly integrate IAQ and to deal with it in the same way that we deal with other issues like the energy use of buildings and like environmental impact. So it's clear that we know that energy and atmosphere are important in buildings. We've done a lot of things over the last several decades to promote energy conservation and to protect the environment. We've had a lot of progress on the efficiency of the various components that go into a building, from envelope components, the insulation, the facade components, to mechanical components of the HVAC system, lighting. We've worked on a system level to reduce the overall energy use of buildings by coordinating how all of those components work together. And then in the environmental realm, we've had international accords on protection of the stratospheric ozone layer, on reduction of carbon emissions, for mitigation of anthropogenic climate change, and have put a lot of effort in development of technology and also in implementation into use of alternative fuels, and even protection of water supplies. That's another coming issue that's going to be very important in the future related to buildings and their use of natural resources. So all of that is ongoing, and it's appropriate because buildings are, in most developed countries, going to turn out to be the largest single user of primary energy. This is called a Sankey diagram, and over on the left-hand side we have the various primary energy sources, from coal through nuclear and renewables and petroleum. And as we go through here, we have conversion and losses and end use over here on the right side. And I've put a little cloud around residential and commercial building energy use in the U.S. Residential buildings about 22%, non-residential buildings about 18%. So at 40% total for buildings, that's larger energy use than either industrial or transportation energy use. So this is the place to focus, or one of the main places to focus, if we're going to try to reduce energy use and emissions from fossil energy use. And a lot has happened to try to promote that. You'll be glad to hear I'm not going to summarize each of these regulations and agreements that are shown on the slide. The point is to illustrate that in the U.S. we have had more than a decade, 2 decades of legislation directed at reducing energy use, and of course you're familiar with things like the European directives on energy, Montreal Protocol, Kyoto Protocol, on the protection of the environment, and organizations like ASHRAE have weighed in here too. ASHRAE has something called the Vision 2020 document, which is a board of directors approved document that expresses a commitment to developing technology by 2020 that will enable the design of net zero energy buildings by 2030. So we're part of that whole 2030-ish movement that has been going on for some time, although 2020 is getting closer every day. When we look at where that energy that goes into buildings winds up, more than half of it goes into various kinds of environmental control. The pie chart over here on the right-hand side shows the average of all buildings in the U.S. from some data compiled by our Department of Energy, and picking from some of these and adding them up, space heating, lighting, space cooling, ventilation, we wind up with over 50% of the total energy use, and almost half of that is HVAC. So most of the energy use that we're seeing in buildings is for the purpose of controlling environmental quality. Which leads to the next point, which is that we can't optimize energy use or emissions from buildings without the constraint of indoor environmental quality. The World Health Organization has made the assertion that acceptable air and water are fundamental human rights, and I assume that that means the air inside the building as well as the air outside. Bjarne Olesen, who's Vice President of ASHRAE and who's also the lead on the revision of the European Standard on Indoor Environment, made this statement that an energy declaration without a declaration about the indoor environment makes no sense. It doesn't, because we're using energy to control the characteristics of the indoor environment. If we're not controlling them to the right targets, then what we're doing really is a fool's errand. So let's move on to several different ways of looking at the impacts of indoor air quality, the cost of air quality, and then look at how we control it and whether we're doing a good job. We could make an example of a particular widespread health problem like asthma, disease that's not really caused by indoor air contaminants, but if you have asthma, asthma attacks are triggered and made worse by indoor air contaminants. It's a huge problem around the world, in developed countries, in developing economies. In the U.S., Centers for Disease Control have collected data that shows that nearly 10% of the population is affected by asthma attacks, results in more than 10 million missed school days, so has a significant impact on the educational enterprise. 14 million missed work days, big impact on industrial productivity. 500,000 hospital stays, medical costs, personal costs, and over 3,000 deaths a year. So this is a very serious problem, and it's to a large part made worse when we don't control a lot of the common indoor air pollutants like tobacco smoke, various allergens from insects, mold, spores, and the like. So these are things that we can do something about with various indoor air quality control technologies. Another way to look at this is in economic terms, and we can do that on the grand scale, the whole country or the whole world, or we can do it on a more microscopic scale. From the policy influencing point of view, you want to come up with really big numbers that relate to the national scale. William Fisk at Lawrence Berkeley National Labs is a very well-known Department of Energy air quality researcher who's been trying to connect these issues for years, and he put together a nice little article that was published in the ASHRAE Journal a few years ago. The case that's made here is still relevant, although the numbers need to be updated periodically, which I've done. What was done in this study that's summarized here is to look at what they consider to be feasible, cost-effective improvements in indoor environmental quality and what the consequences would be in things like improved productivity, reduced healthcare costs, reduced sick building syndrome symptoms, and that's summarized here. Some of this is lighting and comfort, but the rest is air quality, and we get a range of 55 to 308 billion US dollars per year if we did things that we can afford to do to improve indoor air quality. So there's a huge cost there that is being incurred every year, but we're not really counting it and accounting for it. If we did, it would make us spend money on making air quality better. So we need to look at that kind of data. And I should say that I met with the Environmental Protection Agency about 3 weeks ago in Washington, D.C., and I asked them, are there any legislative programs that have to do with air quality in buildings? Because we were having a talk about advocacy, and said, well, you know, if you're going to go and talk to people on the Hill, you should do it to support programs. And not only do we not have any now, they're not aware of any programs that we've had that have been directed at making air quality in buildings better, but we have all sorts of programs that are targeting carbon emissions and energy use reductions in buildings. So we have an education job to do with our people in government. The other end of the telescope, so to speak, is to look at what happens in an individual building. To calculate the costs of poor air quality in a building is actually a pretty complicated thing to do, and I'm not going to try to do it here in this example, but one way to put this in perspective is to look at the cost of energy in a typical building in the U.S. and the value of what goes on in the building, the salaries that are paid to workers, the value of their work product, the cost of their health care. Typically, we would say that $2 a square foot, somewhere 10, 15 euros per meter squared would be a typical energy cost per year in a building. We get 2 orders of magnitude potentially difference in cost when we look at the value of what goes on in the building. So if we could spend a little more in energy cost to make a small improvement in productivity or a reduction in healthcare expenses, in an economic sense, that could be a very good thing to do. The problem that we have is that to go to a particular building owner today and say, if you spend X pounds more on your building, you will get Y dollars in annual healthcare benefit or an annual productivity benefit, is something that we're not able to do with much confidence. I'll come back to that point later, but that is another way of looking at it. And one more thing I should mention is that this is an issue that's not simply an issue of the developed world and one that we can always frame just in economic terms. There are estimated to be 2 million deaths a year due to indoor biomass combustion in developing countries, and that's often women and children because they're indoors and exposed to the cooking fires and heating fires more than men are. So there are lots of different ways to characterize it, but you have to come to the conclusion that there's a huge impact of indoor air quality on the quality of our lives, on our health, on our productivity, and perhaps we should be doing more about it. You might agree with me by the end of this talk. So what do we really know about indoor air quality that we can take to the level of practice and apply in buildings? Not the research knowledge that's in journals, but things that we actually know to a degree of certainty that we can put them into a design standard or into a guidance on best practices. We know that if buildings are wet, that they tend to have air quality problems. Mold grows and produces spores, and that generally is associated with perception of bad air quality. We know that there's a relationship between ventilation rate and perceived indoor air quality. Generally speaking, if we ventilate more with outdoor air, we remove indoor contaminants, and the air quality tends to be better, and the consequences for the occupants tend to be better, although not in every case. We know that building materials have an important part to play in indoor air quality. Carpets can collect all sorts of things and become sources of self-exposure. The carpet, it makes cleaning easier in some sense because it looks cleaner longer, but as I'm walking around, I'm scuffing the carpet a little bit, and I'm pulling contaminants into my own thermal plume, and they're coming up into my breathing zone, and I'm exposing myself to those things. If we had a different floor surface, if it was cleaned regularly, if it was concrete or something like that, stone, it would have a different impact. And of course, the carpet has resins in it, glue that holds it onto the floor, and that off-gasses volatile organic compounds. So there are all sorts of chemicals that are associated with indoor emissions that have negative health effects, and there are chemical processes that go on indoors when we bring in ozone from outdoors that also contribute to secondary air pollutants. So we know those things, and those give us some general guidance about how to design and operate buildings, but what we don't know is enough to have a true performance-based approach to indoor air quality yet. To do that, we would need to be able to measure the things that we were concerned about indoors. There are thousands of them, and we would have to have known safe levels for those contaminants, and not one by one, but in a soup where we have many air contaminants at very low levels. The standards that we have from NIOSH and ACGIH bodies in the U.S. that establish levels for occupational exposures give us limits for a certain number of chemicals that are used commonly in industry, and there are levels at which you get significant health effects. That's far above the standard we would have to apply for everyday indoor air quality when we're exposed all the time. So we're not there yet. What do we do? Because we know that there may be processes in the building that are harmful, we try to get rid of them if we can. Source control, removing a source of a known contaminant is the best thing to do. If we can't do that, then we ventilate it locally because that's going to be the most efficient. If it's something like a process going on in a laboratory, we put a hood over it, and if the contaminants are distributed in nature, like the bioeffluent that we're all putting out or whatever is coming out of the carpet or the paint on the walls, we try to remove that with general ventilation by mixing outside air with the room to remove those contaminants of indoor origin. And we also make some effort to control particulate matter indoors, but frankly, the level of filtration that's historically been used in ventilation standards has been at a level that controls particles that are associated with the clogging of HVAC components and with smudging of surfaces in a room, not particles that are associated with health effects. So 10 micrometers and larger, pretty good control with those filters. 1 micrometer and smaller, not so good. And increasingly, we're doing a better job, I think, of controlling moisture in buildings, both in the way the HVAC system is designed and also the way the envelope is designed. So there's a job here for the architect and for the designer of the mechanical systems, if the building has mechanical systems, to work together on that issue. But probably the most important thing to point out here is that more than anything else, we depend on ventilation when a designer selects a mechanical system. They think mostly about ventilation in terms of controlling indoor air quality. And the basis for the ventilation rates that we use, whether it's in the ASHRAE standard 62.1 that's used in the US mostly, and the European standard, it's based on a subjective impression of acceptable indoor air quality. Here's the definition of acceptable indoor air quality that comes from ASHRAE standard 62.1. The nod to actual health effects of contaminants is right here. The air is acceptable if we don't know about anything that's there in a harmful concentration, if somebody has figured out that there is a harmful concentration. To give you an example of one contaminant that we actually have dealt with based on that principle, standard 62.1 no longer allows for indoor smoking at all. At one time, the ventilation rates that you would find that standard said allows for a moderate amount of indoor smoking, back when that was permitted in most buildings. At some point, it was concluded that there are no cognizant authorities who have established any safe level of exposure to environmental tobacco smoke because it has hundreds of different chemical compounds in it and fine particles and all sorts of things. And so the decision was to just write it out of the standard. But there are a lot of things indoors that may be harmful, and nobody has determined what the level is. So that's a very weak criterion. What we really rely on is the same sort of thinking that we use when we determine conditions for thermal comfort, temperature, humidity, air movement. The conditions are comfortable if you think you're comfortable. So what we say when we're dealing with air quality is if you think the indoor air is okay, then it's okay, subject to that one constraint. And so we can do experiments, and others have done experiments, to determine what the ventilation rates are that will lead to a certain level of satisfaction with the quality of the indoor air. And the place that they started was with the ventilation required to remove the self-generated pollution, the bioeffluent as it's usually called. So we have here a plot of the percent dissatisfied with air quality as a function of ventilation rate, where the only pollution source is the sensory load produced by one sedentary adult. So that's 1 olf. And so each of you sitting there is putting out 1 olf into this room. And what was found was that if you ventilated about 7 liters per second per person, you would wind up with about 20% dissatisfied. And if you went to 10 liters per second per person, you would get to about 15%. And that more or less is the range within which we ventilate in buildings with our minimum design standards. So remember those numbers, 7 and 10. We can extend this concept to the building fabric and to other things that go on in the building by analogy. We can do the same kind of experiments about blowing air through dirty carpet, which has also actually been done, and determining what ventilation rate corresponds to a certain level of satisfaction. And from that, we can infer how many olfs of sensory pollution come from the building. So we can add together the two pieces, and that's what these standards do. This is the table that gives ventilation requirements from ASHRAE standard 62.1, and we have a people rate and an area rate. So we multiply the number of people at design in the space by 2.5 liters per second per person if we're ventilating a jail. And we allow 0.6 liters per second per square meter of the floor area. For different types of occupancies, we have different rates. For daycare, for sick room, twice as much as that. So these rates vary. We come over here and see what we get for typical occupant densities, and we've got numbers like 4 to 9 roughly range. This is just a small part of the table. But so these are getting us more or less in that range of 7 to 10. So are those comfort or subjective acceptability-based ventilation rates that also correspond to anything that's near optimal in terms of health or productivity? That's really a fundamental question, is do we have the right basis for determining minimum ventilation standards? So I'll show you here some research results collected by others, mainly Bill Fisk at Lawrence Berkeley National Lab, that shed some light on this. So we can start with sick building syndrome symptoms. Sick building syndrome is when occupants of a building in large numbers experience symptoms like eye, nose, and throat irritation, headaches, malaise, and those symptoms tend to disappear when they leave the building. I have all of those symptoms at about 4 p.m. on Friday, and they disappear as soon as I go across the street for a beer. But so we've done studies that look at the prevalence of those symptoms based on ventilation rate. And in this figure, the reference point is 10 liters per second per person, 7 is up here. So if we go from 10 to 20, relatively speaking, we get 75, 78% of the symptoms reported that we would at 10, and we've looked at the difference between 7 and 20, factor of 3 difference in ventilation rate. We've gone from 1.2 down to about 0.75. So there's a huge difference there in these symptoms that result in declines in productivity and in absenteeism from work. So that doesn't look too good. What about productivity? There are a couple of different ways that productivity has been studied. Most of the studies have looked at the easy way of doing it, which is looking at relatively low-level tasks. So how many repetitive actions can you do in a certain period of time? So in a call center, how many phone calls is someone answering on a service line, or what's the typing speed and accuracy of a typist in a typing pool? And the studies here give us a similar result to what we just saw for sick building syndrome symptoms. For double the typical ventilation rates to triple, we're still getting significant improvement. It's actually only 2 or 3% here in these studies on these repetitive type of tasks, but 2 or 3% as a percentage of a profit margin for a company is fairly significant. So while it looks like a small number, it's actually quite significant. This is a representation of the results of a study that was intended to look at the impact of carbon dioxide concentration on decision-making ability. So this addresses 2 issues, and it shows in a little different format, but it's looking at one, the question of whether CO2 is really a contaminant indoors. Many have said for a long time, and I've said it myself, that at the concentrations that we normally find carbon dioxide indoors, it really functions more as a tracer gas. It's a marker for how well we're ventilating, and it gives us an indicator of how much bioeffluent is being generated. But the CO2 concentration itself at 1,000, 1,500 parts per million isn't really an issue from a health or performance point of view. That assumption is questioned here, where they looked at the performance on some tests of decision-making ability at 600 parts per million, 1,000 parts per million, and 2,500. 600 to 1,000 is a range that you'd find in many buildings that are ventilated to the standards that we're looking at here. 2,500 is a bit off the chart, but there are many buildings that are poorly ventilated that have that kind of indoor concentration. And we have activities here from focus to task orientation to information search, etc. You can read the paper if you want the full details. And up here is 600 parts per million is our reference, and we see that 2,500, the black circles, that we have very clearly a degradation of performance. But probably the most surprising thing is that there's statistically significant reduction in performance even at 1,000 parts per million. At one time, you could comply with ASHRAE standard 62.1 by maintaining 1,000 part per million concentration of CO2 indoors. So if further studies of this effect confirm it, perhaps it's even worse than I've been painting with some of the earlier data. We may really have to rethink our minimum ventilation requirements, because they're having a significant effect on performance. And finally, what about incidence of disease? That's another thing we could look at. A well-known old expression for estimating the impact of ventilation on the probability of infection is the Wells-Rowley equation. This was developed by some researchers at the Harvard School of Public Health. It's not the latest technique, but it's still widely used because it's simple and it relates the amount of infectious material being generated in a space and the ventilation air change rate, the probability of new infections. So this, based on data, shows that the more ventilation you have, the lower incidence of new infections in an epidemic. That's backed up by real data. This is a study by Yuasia Sun and colleagues at Tianjin University. They did a study where they collected data on the incidence of colds in students in dormitories and compared that with the ventilation rates in those dorms. So here we have ventilation rates varying from under 1.5 liters per second per person to 5. So from really low to pretty good. And what we see is a pretty clear trend of increasing incidence of colds. The thing I want to point out here is that what we're seeing here is a percentage of the occupants of those dormitories who had more than 6 common colds in a 12-month period. Can any of you remember having had 12 colds in 1 year? And can you imagine what the impact of that would have been on your performance in school if that happened during the academic year? So there's lots of evidence that our ventilation rates are perhaps too low from the point of view of preventing infections as well. And we could go on, but we won't because I want to only take 45 minutes. Are we doing enough to wrap all of this up? Probably not. What really happens in the design process, as I see it, is that we pretty quickly get beyond the air quality part of it. We go to the standard and look up how much outside air we have to have for our HVAC system, or we size the openings for a natural ventilation system, and we assume that we've met the bar for good air quality, and we move on to energy and to using alternative fuels and all the other good things that we do to save the environment, and miss the most important thing perhaps from the human point of view up front. So I think that we have an undereducated design community, undereducated owner community, undereducated regulators, and we're just ignoring the fact that there's a big body of evidence that shows that the ventilation rates that we're using, just as one example of maintaining good air quality, are not sufficient to get us very close to optimal performance in a building. IAQ is also connected with the broader indoor environmental quality issue, and we can show that here through some data on thermal comfort. Here's a chart that shows relative performance as a function of the temperature in a space, and we can see that both too cold and particularly too hot, we get reduction in productivity as the temperature changes. So we get the same kind of effect there too. So if we're only designing for 80% satisfaction thermally, and we're designing for 80% satisfaction in terms of air quality, all of these things add up and they give us a very poor overall result. But to tie the two together, there's actually a direct link between thermal environment and perceived indoor air quality. Studies have been done to look at the reporting of sick building syndrome symptoms as the temperature changed, and above 22.5 C, you get about a 12% per degree increase in reported symptoms. So just by being in an environment that's too warm, people will tend to perceive that the air quality is bad as well. So that's the case for the importance of air quality and for the fact that we're not doing enough about it. What can we do now to be able to provide better air quality in buildings with technology that's available? Here's a quick list of a few things, and we could add some more to this. I think I've left natural ventilation off. Energy recovery from ventilation air is an obvious one that's required by standards now in many cases. We can do that as efficiently as we want to. Allowance for intermittent occupancy. If we really understand the ventilation standards, we can reduce the amount of outside air we bring into spaces where there's irregular occupancy by averaging. You can average over about a time constant for a space, maybe 3 hours or so, and use that to reduce the peak ventilation amount that's required. We can also try to sense the number of people in a space and control the ventilation based on occupancy. We saw the table earlier that said 2.5 liters per second per person or 5 liters per second per person. If we can do a real-time count of the people in a space, then we can modulate the outside air to provide that 2.5 or 5 in an ongoing way, with the outside air being reduced to what it needs to be. The problem with this is that it's generally done with carbon dioxide measurements, and there are a lot of practical problems with that, but that's really another talk to get into the details of why carbon dioxide demand-controlled ventilation often doesn't work as well as it should. And we also have things like dedicated outdoor air systems, outdoor air units that only provide the ventilation air that incorporate total energy recovery, so both sensible and latent heat using enthalpy wheels. If we take that kind of a unit and combine it with a hydronic cooling system, for example, we reduce the transport energy that's required greatly because it's a lot more efficient to deliver the heating and cooling energy through a water system than to do it with low density, high volume forced air. And we wind up with good ventilation and lower energy use in many cases. Something that is done in some cases but not enough is the use of air treatment as either a substitute or a supplement for ventilation. Obviously this can be done because we have submarines and space stations where there is no ready supply of ventilation air. So if you have enough money, you can build a system today that will allow you to exist without any ventilation. But between that and what we're doing in most cases, it's possible to enhance air quality without spending as much money as you would spend on ventilation air. That's a point that I really haven't stopped to make very clearly, but ventilation, while it's a common solution, can be an expensive one, particularly in a place like, let's say, Doha or Kuwait City, where they have summer temperatures that get into the high 40s C. Sounds like a good solution up here in the north, but in some places even that isn't good. So I think we're going to see more of control by air cleaners in preference to ventilation in those sorts of environments. All this kind of technology is available today. We can apply it if we understand what we're doing. It's permitted by our ventilation standards and it's encouraged by our energy standards like ASHRAE 90.1. So I could give you a whole hour on each one of those, but for now our list will have to do. Some organizations that are trying to push the quality of buildings in a variety of ways have recognized the importance of having better indoor environmental quality. The LEED rating system is not really a standard, but it's used so widely that it almost seems like that at sometimes. And LEED has decided some years ago to give an extra credit if you increase your ventilation just 30% above either the European or the ASHRAE standard for ventilation. It also gives credits for demand-controlled or dynamic ventilation, for natural ventilation, and for using low-emission materials. And removing pollution sources from the building is the best way to improve air quality because it doesn't cost you anything in terms of additional energy for ventilation or for air cleaners. All right, so now let's move to the final topic, which is how we get to the point where we can treat air quality with the same sophistication and the same effectiveness that we deal with things like energy use of buildings and emissions now. The current situation is that we have an imbalanced situation for air quality versus energy. Designers really don't think about it as much as they should. They don't have the tools to address it the way that they should, so the effort goes into what's being promoted today, which is efficiency and emissions. Part of the problem is that we don't have the tools. We've spent decades developing load calculation programs and energy simulation programs. I know because we were working on the precursor of the Energy Plus program when I was a graduate student at the University of Illinois back in the 1980s. And some of the same guys were my classmates back then are now the developers of the program today. So it's a long history, and even energy analysis isn't where we want it to be yet. Imagine, given that we've only just started on air quality, the effort that's going to be required to catch up. So we don't have those tools. One reason I would submit for that is that for the most part, the air quality and energy worlds are separate. There are a few people that straddle that line, hopefully an increasing number, but to a large extent, air quality is the realm of scientists who have credentials in things other than engineering, environmental health specialists, and others, while engineers tend to like to do the thermal things. We need to bring them together. If we did that, we might wind up with something like we see here, and I actually understand that some of the research going on at UCL is working on this very issue. I'd like to see an analysis that leads to the selection of building systems that integrates energy and air quality. We'd have to start with an expanded view of the design scenario. When we do modeling now for buildings, it really generally means energy modeling, and we worry about two things: meeting the requirements of the standards for performance thermally, the temperature and humidity set points, and having the design ventilation. And then we calculate the capital cost of the systems and the energy cost of the systems, and we're done. What we need to do is to put the air quality parameters into this scenario and go beyond the energy simulation to first model the contaminant exposures that occur in the building. That takes tools like multi-zone models or maybe computational fluid dynamics, although it's not really to the point of being practical on a whole building level for complex buildings yet. And then we take that exposure data and use dose response models to determine what the impacts are on the people in the building. We can calculate the value of that, and we can incorporate that information along with the energy use information and the capital cost to get an economic analysis that is more comprehensive and gives us a better overall result. But we're not to the point of doing that yet in the practical realm. There are a few commercial packages that are trying to address this, but they aren't the sorts of packages that every designer is going to be picking up off the shelf and using tomorrow on their next 500 square meter commercial building. There are some research studies there that show the potential of this method in different ways, and I'll give you a quick look at three of them here as I wrap up. One is a study that looked at the effects of the excess ventilation from using air-side economizers on sick leave in a building. So air-side economizer, in case you're not familiar with it, is a control strategy for an air handling unit that conditions a building with a stream of conditioned air and brings in the ventilation air. If the outside conditions are favorable, if the outdoor is cool, if it's low in humidity, you can bring in more outside air and reduce the amount of mechanical cooling that's required. That's actually a standard or code requirement in a lot of systems. We know that saves energy. Question is, how much does that extra ventilation associated with increasing the outside air improve the productivity or reduce the sick leave of the occupants? So Fisk and Faulkner and Sepinen and Wang did this study of economizers applied to a building in Washington, D.C., hypothetical building, and used the Wells-Riley model to estimate the impact on the incidence of illness and translated that into a sick leave cost reduction. So here are some of the results from that paper. This was in ASHRAE Transactions a few years ago, the conference proceedings. Building that was designed for 10 liters per second minimum ventilation, typical standard sort of level. The energy savings for that building over a year with an economizer were $1,900 US. Using the Wells-Riley analysis with some uncertainty applied to get upper and lower bounds, $13,000 to $16,000 per year in healthcare benefit. So it's a 3 to 8 times greater benefit for the impact of better air quality from more ventilation than from the energy savings, and yet this cost is never calculated, and it's not the reason we do outside air economizers. But if we knew that, we might take a different approach to how we design and control our systems. One of my graduate students, Bruno Lee, who's now doing a doctorate at Eindhoven at TUE, applied this same approach to distinguishing between different options for air cleaning. And we were looking at ultraviolet germicidal irradiation or enhanced particulate filtration as a way of controlling infection risks. So we have either UVC lamps to irradiate the air going through an air handling unit or a MERV 12 filter. That's a pretty high efficiency filter rated by ASHRAE standard 52.2, which is widely used in the US by manufacturers now. Not the same as the European standard, but it's common where I come from. So we have a simple recirculating air system here with a pre-filter, minimum code filter, MERV 6, and we would either put a high efficiency filter here in the same airstream, or UV lamps downstream of the cooling coil or upstream of the cooling coil. The difference between putting them downstream and upstream is to get the same effect, it takes nearly twice the nominal lamp power downstream of the coil because it's cold, because it's a cooling coil, and we're operating in this box on the air velocity and air temperature chart, whereas if we're upstream, we get the mixed air temperature outside plus return, and we get a lot warmer temperatures, and our design conditions wound up being different. So that had a first cost impact to get the same performance. So we looked at those three situations and found that for our assumptions about the pressure drop through the filter and the power required for the UV systems, there was about a 10-to-1 difference in the annual energy use, and again about a 10-to-1 difference in the life cycle cost. So an analysis like this could be used to determine which of these technologies is better. And when we carried forward and calculated the health cost impact, $3.50 per square foot compared to 1 to 10 cents per square foot. So again, orders of magnitude difference in the benefit as opposed to the cost of using a little more energy. And the final study is by Johansson, who's a Swede who did a dissertation on this global optimization problem, looked at combining airflow and the value of the work being done in a building and the type of HVAC system to come up with system recommendations, paper in Building and Environment that's very interesting to read. I'll just show one figure from that. This is a figure that shows the optimal, the most cost-effective airflow rate for a system based on the salary of the workers in the building and the type of system. So we have a constant air volume system here where the fan runs flat out all the time, uses the maximum amount of energy. And here we have a demand-controlled ventilation system where we can modulate the ventilation to meet the minimum requirements of the occupants. And what we see are two things. One we see is that for any given salary level, the system that uses energy-conscious IAQ technology allows you to use more outside air for the same investment. And we also see that if the value of what's going on is greater, then you also wind up with a conclusion that you could afford, if you're looking at this in simply economic terms, to use more outside air. So that's my view of this issue. To wrap up, maintaining even the level of air quality that we have in buildings today is energy intensive and costs a lot of money, and I think it's pretty clear that it's mediocre at best. So why don't we do better with the technologies that we already have in front of us? We can, and it will pay us back many times over in occupants who are more satisfied with the buildings, that get more work done, that are sick less. Problem is that to get there, we need to get these IAQ and energy worlds together to give us the tools, the educational materials to be able to change the way practice is done so that we can do the analysis to design these better buildings and systems. So that to me is one of the key needs, is to improve the status of tools, and some of the research that we're doing today in our lab is directed at integrating IAQ analysis with energy, and hopefully we'll be publishing some of that stuff, and more importantly having better tools in the hands of the designers in a few years, which is really the more important goal. So with that, I'll conclude, and thank you for your attention.
Bill, thank you very much for what was a very interesting and clear presentation. I hope you, well, one of the graphs that we'd be particularly interested in is this one of CO2 and the impact of CO2 on cognitive performance. I hope you appreciated the fact that we tried to recreate that experiment this afternoon in our meeting room, where we succeeded in getting the CO2 levels up to 5,000 parts per million.
Yes.
And I think where we very clearly showed that basic strategy became dysfunctional at those levels.
Yes.
CO2. Any questions? Gary.
Oh, you call. Yeah, I'll just answer.
Gary Raw from the Energy Institute here. Great to hear ASHRAE still interested in IAQ. I was very much part of that scene about 10 years ago, more into energy now. Since Tad has raised that CO2 study, I was wondering if you could answer a question about that, which I haven't really caught up with. Mm-hmm. Was that laboratory study with everything else controlled, or was it going out into actual buildings?
Yeah, it was a highly controlled study. So there are good things about doing that, and not so good things. But they were in I think the stainless steel environmental chambers, and they were putting in pure CO2. It's an interesting read. You should pick up the paper. I'm happy to leave the slides so you can get the references if you'd like to do some more reading.
My name is Rian. I was wondering, now if you want to have a solution for the hot air regions and the desert regions, are we still having the opportunity to increase the airflow from outside to enhance the ventilation inside?
The economics of increased ventilation are much worse in hot climates. In fact, one of the things that I teed up as part of my presidential year this year is a conference in Doha in April on IAQ and energy in high ambient climates, where they're going to be talking about exactly that issue. I think we really need to look more at recirculation and air treatment in those cases. Also because in those climates you can have dust storms, very fine particulate matter. I lost a camera on my last trip to Kuwait to one of those dust storms. I thought it was fog, it was so fine.
Yeah,
Tim.
The benefits you've shown already are massive in terms of productivity, but I guess the challenge we have is that although the perceived benefits may be huge in productivity, the operational cost of a building and salaries perhaps just swamp those benefits. So it's very difficult to convince the end user that there's this possible benefit in productivity. But of course, the whole cost of running a building is so huge. It's difficult to actually discriminate.
Well, it's back to you can't manage what you don't measure problem. You just imagine if you were in a country where you really weren't responsible for your own energy bill, where someone just disconnected your energy meter and they were paying your energy bill. You would only be concerned about the cost of the equipment that you were putting in the building, and that's the problem we have with air quality. We don't have a productivity and sick leave meter on the building unless we're measuring those things. So in a business environment, we get the data that convinces us that this might be a good thing, but especially in a medical environment, they're very aware of incidents of infection and how different practices affect it. So that's the problem. And as I said before, until we get to the point where we have enough confidence in the kind of results I'm showing to be able to standardize them, to say if you increase your ventilation by so much, you're going to reduce your sick leave or increase your productivity by a certain amount, and you can put a financial value on that, I think it's going to be a hard sell if economics are the driver. Yes.
I think in the UK there's some limited but encouraging evidence that the UK government, the Department of Energy and Climate Change, requesting evidence to perhaps try and better understand the links between energy efficiency interventions, particularly in dwellings, and the potential impact on health and the desire to monetize those impacts and include a wider economic analysis. I just wondered if you, in your travels as President of ASHRAE, you were seeing any similar requests from governments around the world, or the States perhaps, to acknowledge that those potential links.
Not to the extent of an actual effort that's underway, but I am finding that there's starting to be some awareness of it, so I'm hopeful that that will be the next trend. ASHRAE is working in the U.S. to get that message to government so that they will look at it. In fact, if I can tell one more story, I went to a meeting of all the armed services in the U.S. because they're the biggest landlords that we have, and they're using ASHRAE's sustainability standard 189.1 as a basis of a design for their facilities now. And they said, well, we go to the Hill and we sell this on the basis of cost effectiveness. And I said, well, you mean you tell them if you ventilate more like the standard says that they're going to get better performance? So, oh no, I mean if one guy is sick, we'll just send another one. It's all energy and water. So that's the problem, that even the concept of sustainability really boils down to energy cost in a lot of people's minds. That's something we've got to work on. Yes.
Alex McMillan, I'm a public health doctor here at the Bartlett School of Graduate Studies. I had a kind of comment more than a question, but I wonder whether when we are comparing the energy cost as an environmental cost against health costs of indoor air quality, we're forgetting that the energy cost will turn out to be a health cost. And therefore, if we're going to compare them on equal ground, where we need to count the energy cost as a health cost.
Oh, so you're talking about health effects of emissions from fossil fuel combustion? Sure. That's true, but I'm aware of that already happening. I was just at a meeting over in Brussels last week, and someone from the European Commission was there, and they pointed out to us the health effects impacts of reducing fossil fuel use. So I agree with the point, and my question is, why are we doing it outside and not doing it inside?
And so it may not be very important where it's clearly, they're clearly moving in the same direction as co-benefit, and when we have to trade off perhaps health costs and climate mitigation, then it becomes problematic how we cost up those things as health or environmental costs.
Well, it is going to boil down to what do you value and what are you going to optimize. I think if you start from the point of view of people, that's one way to do it. Another is from the environment generally, but you have to set some standard there. What we're doing now with air quality has nothing to do with health or productivity. It's just based on subjective perception. I think we should at least start to look at it from the health point of view, and then deal with these issues like what are the overall impacts of it. Yeah, thank you.
Another, if no one else, you mentioned briefly reducing emissions from indoor, accepting that's slightly off to the side of ASHRAE's remit, I guess, unless those emissions are coming from the building services. How big a contribution do you see that making? I mean, you talked about integrating in a formal way the IAQ and the energy models. How bad do those models have to be before they're not better than doing nothing? I can put it that negative way around. Even a poor model could be better than at doing nothing about IAQ and energy.
I got lost somewhere in the question. We were talking about indoor contaminant emissions from materials.
Yeah, we know we can do a lot about emissions without having a better model. And it seems to be an obvious way to go.
That's true. So just do it if you can. Remove sources of contamination, substitute materials, because we know it's going to be better. We don't need a model to know that it's going to be better, but I think that it needs to be our goal as engineers and architects to try to quantify it. And that's,
as a psychologist, I agree.
Yeah, and psychologist, and whatever other discipline you may be in here. That's a diverse audience.
Okay, well, I'll take the chairman's prerogative to ask the last question then. I was fascinated to see that LEED was taking into account a 30% change in ventilation rate. Is anybody in the States able to measure a 30% ventilation rate in practice? Because I'm not sure we are.
A 30% change,
Yes.
yeah. Well, yeah, that's another subject altogether, is that it's great to have criteria and standards, but I think it's essential that we go out and measure what buildings are doing, not just commissioning at the time of occupancy, but in an ongoing way. The base study that was done in the US a few years ago measured 100 commercial buildings, and they were all off by huge amounts from their design outside air flow rates. So there's a whole world of real building issues out there that can't be addressed just by our design perspective.
Great, well, thank you very much for
Yeah, thank you.
a fascinating presentation.
Yeah, my pleasure.
Also the answers to questions.